So what did we prove in this case? Well, we wanted to figure out 2 multiplied by itself, how many times will give me 23. Now we know that to the 4th power it was too small, to the 5th power it was too big, so we used some algebra and figured out that that exponent should be about 4.524. So in other words, 2 raised to the 4.524 power should give me about 23. Well, there I see that it gives me 23 and some change, which is perfectly fine because that gives us a lot closer than using 4.55 as the exponent. Okay, so let's just try to name some variations of being able to convert from exponential to logarithmic form. So this will be helpful. Exponential form and then the logarithmic form. So depending on what we're trying to solve, these 2 forms are both valuable. So let's say that we have, we want to solve, or we're looking at 2 to the 3rd equals 8. Well, in logarithmic form, we say that we start off with the exponent. So 3 is the exponent, the log, on the base of 2 that gives me 8. So to prove that 3 should be the power, in my calculator I would do log 8 divided by log 2. Again, that's something that you'll establish later on in a later class as to why that works, but just to verify, log 8 divided by log 2 should give me 3, which it does. So that's just a way to confirm that we're getting the right answer. Similarly, there's really no reason why we would want this in logarithmic form because we already know the answer, but this is just a way to get you to think in both directions. So let's say we have 16 equals 4 squared. Okay, well, probably easier to rewrite it so that you can look at it from left to right, but that's up to you. 4 squared equals 16. 2 is the power on the base 4 that gives me 16. Sometimes we'll read this as 2 equals log base 4 of 16. 2 equals log base 4 of 16. So right now we're in base 4 format. Again, I could verify this, that this gives me 2 in my calculator by doing log 16 divided by log 4. Let's do a couple others. Well, what if we wanted to solve 5 to the x equals 16? Well, I know that 5 squared, or 5 to the 1st gives me 5, 5 squared gives me 25, so x is going to be somewhere between 1 and 2. Well, I can't really solve it this way unless I just do guess and check, so I'll convert it into log form. I get to isolate x because it is the exponent on 5 that gives me 16. So in my calculator, I would just do log 16 divided by log 5. I would hit enter and that would give me about 1.7. So x should be about 1.7. Again, that's with some rounding error, so if we wanted to be more accurate, we could round that out to more decimal places. But that gives us the basic picture that 5 raised to the 1.7 should give us about 16. Now you notice that with that rounding, we're kind of far off, but if we did 1.72, we'd be a lot closer. We'd be at 15.9. So maybe we should do 7227 to be pretty accurate. Now similarly, we could go backwards. We could say let's convert from log form into exponential form just as a good practice. So if I had 8 equals, no, let's not do 8, let's do 16 equals log base 2. Sorry, here, let me make a modification. 4 equals log base 2 of 16. So what does that mean? Well, 4 is the exponent on 2. So 4 is the exponent on 2 that gives me 16. So 2 to the 4th power equals 16. Let's do another one. Well, what if we knew that, let's say, 3 equals log base 3 of 27. This means that 3 raised to the 3rd power equals 27. So 3 is the exponent over 3. That gives me 27. Well, where would this come in handy? Suppose we had a logarithmic equation to begin with. So let's just say that 4 equals log base x of 15. Okay, well in this case we want to isolate x, so it would be useful to go back into exponential form because we know that 4 is the power on x that gives me 15. So now I could solve using whatever rules I need, in this case raising both sides of the 1/4 power. Or better yet, what if it were this? 4 equals log base 2 of x. Well, what's this asking for? Again, I want to be able to isolate x, so I would say that 4 is the exponent on 2. 4 is the exponent on 2 that gives me x. Oh, beautiful. Okay, so I've already isolated x. Now I just need to figure out what 2 to the 4th power is. 2 times 2 is 4, times 2 is 8, times 2 is 16. So x would equal 16. So it's kind of convenient going back and forth between the two notations. Now, as one final note, what if I have something like this? Let's say we know that in an interest problem, you put $185 into an account earning 4.5% APR compounded monthly. You want to know how long will it take you to earn $500. Okay, well I'm going to not have to intuitively develop this thing all the time, I know that compounding is occurring monthly, which is not continuous, so I am going to use my compound interest formula, which we've generically written like this. Well, I know that my present value is $185. I know my future value will be $500, and I know my rate is 4.5%, which, remember, as a decimal, if you divide 4.5 by 100, gives you 0.045. And I know that I'm compounding monthly, so remember that monthly compounding means 12 times per year. So I plug in what I have, and this gives me 500 equals 185 times 1 plus the rate, which is 0.045, broken up into 12 equal pieces, so I get a monthly rate, raised to the 12. Well, I'm trying to figure out how long, so I don't actually know what t is. That's the number of years that I'll need to be investing for. So if I come over here to my handy calculator and I just work the inside out a little bit, 1 plus 0.045 divided by 12, that tells me that I would have 500 equals 185 times, in my parentheses, 1.00375 raised to the 12 times t power. Okay, well now I realize that I'm going to need to isolate this t. I'm going to need to bring it down. So I can do it two ways. One, and this is typically an okay way, is to solve it graphically. Plot this equation, plot this horizontal line 500, and see where the two intersect. I'm going to do it algebraically. So if I were to put something in for t, my order of steps would be raise 1.00375 to the 12t power. My second step would be to multiply by 185. Now, since I'm working in reverse, in other words, I'm not putting in something for t, I'm putting in something for y, or my output value, so I'm going to need to work backwards. In other words, I'm going to need to start by dividing by 185, and then I'm going to need to isolate t, bring t down. So I'm working entirely backwards here. And so I am going to, now remember this is a multiplication sign, so I need to isolate t. I can begin by removing the 185. That's the easiest thing to do first, and obviously that's the last thing we would have done if we had put something in for the input and solved for the future value. So in this situation, we would find that 500 divided by 185 that I'm basically looking to almost triple my money. 2.7027 is the ratio between what I want and what I start with. The reason I'm doing this is because now I notice that, hey, this can be treated as a logarithmic problem. I want to solve for part of the exponent. So I would say, in words, that 12t is the power on 1.00375 that gives me 2.7027. So what I will do is I will convert this into a logarithm. That allows me to say 12t is the power on 1.00375 that gives me 2.7027. Well, you might say, oh, well, now I have 12t over here. I just want t. Well, that will be an easy step. We'll just need to divide by 12. So the first thing I'm going to do is I'm going to set this up for my calculator. Log of 2.7027 divided by log 1.00375. That's what we need to do to get it into our calculator. So 2.7027 divided by log of 1.00375. That gives us 265.63. So I know now that 12t is about 265.63. So if 12 times the number of years is that, I know that the number of years will be 265.63 divided by 12. Now in this case, 265 is the number of months, because the number of months per year times the number of years will give me the total number of months. But I really want the total number of years. 265, actually I can just do my answer divided by 12 to give me about 22.1 years. So that will take a very long time. But again, we could have done this with the calculator, and we should have noticed that it would be about 22.1 years when the investment would be worth 500. But this way we were able to do it algebraically, which is just another strong analytical form of being able to problem solve. So that was our thought process. And notice how we use the idea of logarithms to help us isolate an exponent when it contains the variable. So that's what a logarithm is really used for, is to isolate a variable that's in the exponent. Well, how would we do it if this were compound interest, or continuous? If it had said interest is compounded continuously? Well, we would have used our future value equals the present value times this constant e raised to the RT power. In this situation, my p is 185. Remember, e is a constant, so we don't ever plug anything in for that value. My exponent is the annual rate, which is 0.045. This is the only time that we don't have to divide it, times the number of years, which we don't know at this point. It's just 0.045t. So I will start off this problem in the same way. I'll begin by dividing both sides through by 185, giving me the same value, 2.7027 on the left-hand side. Now again, the first thing I would do if I were plugging in something for t is I would do e raised to that power, and then I'd multiply by 185, and that would give me my future value. Now I'm working backwards, so I'm going to divide by 185 first. And now, don't let this throw you off, you could still apply the same technique. 0.045t is the power on top of e that gives me 2.7027. So in my calculator, I would do 0.045t divided by the log of e. And so to get the value of e in there, remember we said early in an earlier video you can do second and the division sign, and that gives me e. You don't want to use the capital E, because that's a letter. And that tells us that 0.045t is about 0.99425. And I'm just going to take it out to get some good precision on this. And now I'm going to divide both sides by 0.045 since I want to isolate t. So divide by 0.045. And you'll notice that in this case, t is still about 22.1 0.09, or about 22.1.